So this unit is on what's called polynomial functions, and today we're going to begin by looking at characteristics of polynomial functions. The unit in a nutshell revolves around the graphs of polynomial functions, and part of that has to do with transformations of polynomial functions, but that's a very minor, it's a thin veneer on top of everything. It turns out that at the end of this unit, you should be able to plot with unbelievable precision what a polynomial function will look like, even without using your graphing calculator. And you will have discovered by now that, of course, questions that you're expected to be able to complete are ones that are designed so that you can't use your graphing calculator, right? Okay. So today we're looking at characteristics of the graphs of polynomial functions. This is on page 1 of your unit handout. What we're going to end up learning today is just generally speaking what polynomial functions are and what they look like graphically. That's it. When we sketch these things after today's lesson, you're not going to be very precise in your sketch, but they're going to have certain properties that you can look at an overall sketch of a graph of a polynomial function and say, I know that that is this type of polynomial function, and I know the equation will contain this thing and this thing. Okay? So to begin with, we're going to be identifying a function as polynomial. This is something that in the program of studies, which is the playbook for teachers, it says students are expected to do. I don't think I've ever seen a question on an exam that says, which of the following are polynomial functions? But I think it is important that you understand what they look like so that you know when to start applying what we learn about them. If it doesn't look like a polynomial function, but it looks like an exponential function, then you go into a different box of rules to decide what to do. State the degree, leading coefficient, and constant term of a polynomial function. These terms, these words, degree, leading coefficient, constant term, are key. You need to be able to identify what these things are, because once you do that, it tells you information about the graph of the polynomial function. It tells you about the behavior of the mathematics. And basically, from that, you should be able to tell me lots of things. The general shape, what's called the end behavior, how many different x-intercepts there may or may not be, which I admit is kind of vague. So today we're saying, well, this polynomial function may have this many or this many or this many x-intercepts. We will learn later how we decide definitely how many it has. But we will also learn today that by looking at a polynomial function, you'll be able to say it cannot have this number of x-intercepts. So let's begin by going over some terminology. I'm going back to actually maybe grade 9, but definitely grade 10 when you talk about polynomials, because you have a unit in grade 10 math called polynomials. You're taught that there's this thing called a polynomial term. And polynomial terms might have more than one variable. Like 3a squared b is a polynomial term. But in terms of polynomial functions, I'm going to say that a single variable polynomial term, which means every polynomial we look at will have one variable, x or b or whatever the case is. A single variable polynomial term rather, contains a numerical coefficient multiplied by the variable raised to an exponent, and this is key, the exponent has to be a whole number. Some people will confuse the whole numbers, which are 0, 1, 2, 3, etc., with the natural numbers, which are just 1, 2, 3. I have always, and I think a junior high, I think probably Miss Kenny taught us this, I have always learned that whole numbers contain 0 because 0 is a whole. There's a hole inside of 0 when you write it. It's a different kind of hole than the word whole up here, but that's how I remember that. Even as a teacher, if someone says, well, what are the whole numbers? I go 1, 2. Oh, wait, it contains 0, because 0 has a hole in it. So this is I guess maybe a general way of me saying what I just wrote above, that ax to the n, which means a multiplied by x to the n, is a polynomial term. A is the coefficient. X is the variable that we're talking about. And n is the whole number exponent. And I'm including something here that I don't know if you remember, but do you remember the word degree? some of you. When we talk about degree of a polynomial term, the degree is the exponent of that term. So as a further illustration, if I look at the polynomial term negative 4x to the 6, we could say that that's a degree 6 polynomial term, which tells us that the exponent on the variable is 6. Of the variable x, sometimes you will see in the variable x, and that just means the variable happens to be x, and the coefficient of that term is negative 4. And that's just a review from maybe even grade 9 math, because you learn about polynomials there as well. So what a polynomial is, and I can say polynomial and then just write it out, or I can say polynomial function and write it out and say it's equal to f of x. The distinction is not important. What a polynomial or a polynomial function is it's something that contains one or more polynomial terms that are added together. So for example, this is a polynomial function. This happens to be a quadratic function. Y equals, or f of x equals x squared plus 3x minus 1. Is x squared a polynomial term? Yes. It has a coefficient of 1, the variable is x, and the degree is 2 of that term. And then plus 3x, is 3x a polynomial term? Yes. The coefficient of that polynomial term is 3, the variable is x, and the exponent is 1. So we certainly don't need to write this, but if you wanted to, you could put a 1 there. Is the number negative 1, we're adding negative 1, or you're subtracting 1. We'll just go with 1. Is 1 a polynomial term? Well, there's a coefficient, the 1 or the negative 1, depending on how you look at it. There is a variable, and it is raised to an exponent. So when we look at this whole thing, we call it a quadratic polynomial function. The degree of the quadratic term is 2. The degree of what we call the linear term is 1. And the degree of what we're going to call the constant term is 0. So there are 3 degrees in this polynomial function, 2, 1, and 0. G of x equals negative 4x cubed plus 2x squared minus x plus 5. These 4 terms are all polynomial terms. The first term, and I'm not going to do this with every one. The first term has a coefficient of negative 4. The variable is in x, and the degree is 3. The second term has a coefficient of 2. In the variable x is raised to a degree 2, or an exponent 2. The third term has a coefficient of negative 1. Because I've told you it's the sum of the terms, we can say the coefficient of the third term is negative 1. The variable, of course, is x, and it's raised to the 1. And then we have 5 as a coefficient times the variable x raised to the 0. I hope it's clear. I don't really come right out and say this, but a polynomial function has to have the sum of polynomial terms, but the variable in each of the terms is the same. There's no such thing as a polynomial function where we have some x cubes and x squareds, and then we have z squareds and z's. It doesn't work that way. This would be a polynomial function. This would be a polynomial function. I want you to notice with the last polynomial function, with all of the others, f, g, and h, the degree goes from the highest to 1 less, to 1 less, to 1 less, to 1 less, until you get to a degree of 1, and then finally a degree of 0. This last example illustrates to you that you don't have to have every degree represented in a polynomial. This polynomial has a degree 5 term, a degree 2 term, and a degree 1 term, and that's it. This is not a polynomial function because the exponent on x in one of the terms is not a whole number. 1 over 3 is not a whole number. This is not a polynomial function because if I explore what this is, this, do you have an equal sign there? Put an equal sign in there. I redid my note package last night. It was getting late, so there's bound to be a few corrections that need to be made. The coefficient of this term is root 3. I can break that up into root 3 root x cubed. I can do that. That's allowed. And you've learned in previous courses that a square root is the same as saying raised to an exponent of a half. And you've learned in previous course, is that when you have this piece here, it's called, and I've never liked the name for this, a power of a power. Okay? But that's what we call it. And you have learned that if you want to simplify that, you multiply the exponents. And if we do, we get an exponent that's not a whole number. Okay? So that's why this is not a polynomial function. However, and I'm going to do my best to write really small here, if this were an 8, this would be a polynomial function. Because the square root of x to the 8 is x to the 4, and 4 is a whole number. It's not. It's not 8. I'm just saying if it were, it would be. R of x is not a polynomial function because the exponent -1 is not a whole number. And s of x is not a polynomial function because it just doesn't follow the pattern. There's no polynomial terms there. S of x happens to be called a rational function. R of x is also rational. And we will learn about those later in the course. So now the most important terminology for this lesson, which continues into the further lessons. The leading term of a polynomial is the term that's written first if you write all of the terms in descending order of degree. And if I go back and look at these examples I've given you, these are all written in descending order of degree. What I mean is the degree on f of x starts with a term of degree 2, then degree 1, then degree 0. Degree 3, 2, 1, 0. Degree 4, 3, 2, 1, 0. Degree 5, 2, 1. That's what descending order of degree means. The highest degree comes first. Well, if I tell you that the leading term of a polynomial is the first term when written in descending order, I'm just saying it's the term with the highest degree. The degree of the whole polynomial is the degree of that leading term. So, and we have official examples we'll do in a second, but when I take a look, for example, at h of x, we happen to have in h of x a total of 5 terms, and each of those terms we can talk about the degree. The degree of the 4 is 0, the degree of the 6x is 1, etc. But the degree of the whole polynomial is 4. That's what I'm saying. The highest degree rules the roost, metaphorically speaking. And what that means is if the highest degree term is 4, the degree of the polynomial is 4. And it turns out that that degree of 4 in this polynomial tells us about the shape of the graph, and the other degrees don't matter. Okay? The leading coefficient, and I hope this makes sense, the leading coefficient is the coefficient of the leading term. So it's all about, so far, that highest degree term. That's what we need to focus on. Most of the other stuff is filler, and it doesn't really mean much at all in terms of graphs. And then we also want to always look at the constant term, which is the degree 0 term. That's the term whose value does not depend on the variable. So look at the word constant here in the context of some of these examples. I'm going to pick on g of x this time. Well, when I put in different values of x, this is the notion of a function, so you could graph it. You get ordered pairs. When I put different values of x, maybe I generate a table of values. This term of -4x cubed is determined by what I choose for x. If I choose 1, it's -4. If I choose 0, it's 0. If I choose 2, it's -32. It depends on x. Every term here depends on x except for this term, 5. 5 is a constant. It doesn't matter. It doesn't matter what x is. That term will contribute to the whole thing, 5. It's constant. So I guess what I'm saying as well is that the constant term is the degree 0 term. By the way, the degree 0 term of q of x is 0. There is a constant term in q of x, and it's 0. Okay. So let's get some practice here. For these polynomial functions, state the degree, the leading coefficient, and the constant term. These 3 things now, the degree, the leading coefficient and the constant term, I can look at those and I can tell you what this graph will look like roughly. Well, what is the degree? Don't get trapped into just looking at the first term and going, oh, the degree is 2, because I've purposefully written these in kind of a scrambled order. You need to, I really don't think anybody actually has to rewrite this. You can see that the leading term is negative 25x cubed, because that's the term with the highest degree. But if we write it in descending order of degree, we get that. So the constant term, I mean, you ought to be able to tell me the constant term is 2 regardless of how it's written. You can just scan the terms and go, there's a 2 there. The degree is 3, and the leading coefficient is negative 25. Now, when I told you a second ago that it's these 3 things that tell you about the graph, it's really the degree, the constant term, and whether the leading term is positive or negative. That 25 gives me 0 information without further exploring things. It doesn't tell me anything about the graph of the polynomial function. Now, let's FOIL this out. Okay, let's simplify this, because what we would say is this polynomial function in B is a polynomial function in factored form. I'm going to even write that so you can see that phrase. This is the polynomial in factored form. What is the polynomial function if we unfactor it, if that's a word or a process? Well, we FOIL this out. It's 15x squared. My inner, I'll do my outer first, I guess, is 6x. My inner is negative 10x. And then I have minus 4. Can we agree on that? I just don't want you sitting there and writing what I have written down. I want you thinking. So f of x can be written in this other form as 15x squared minus 4x minus 4. So are we in agreement that that is multiplied out correctly? Okay. What we call this, and I've run out of room, so I'll write it down here, is expanded form. That's expanded form. And it's the expanded form that's important. Don't get me wrong. Factored form tells us in some ways a lot more information than expanded does. But that's not what we're learning about today. Expanded form is the form you look at to determine the leading term, so you can find the degree and the leading coefficient, and the constant term. But I want you to understand that what we're going to answer below here, these 3 things, are determined solely by this and this. Correct? That filler doesn't help us. And I want you to notice that this, which is the highest degree term, is the product of the highest degree terms in the factors. If all you're after is the highest degree term in the expanded form, something's funny over here, if all you're determining is what's the highest degree term, you just have to multiply the highest degree terms in each of the factors. That's going to be important for later. And the product of negative 4, which is the constant term, is the product of the constant terms of all of the factors. So we didn't need to FOIL. We could have just flood. We could have just gone first and last. Anyway, the degree is 2. The leading coefficient is 15. And the constant term is negative 4. Are we okay with that? Okay, so if I said to you, I'm going to go here. What does this graph look like? At the end of today, you should know what this graph looks like without using a graphing calculator. And you need to determine the leading term, so you know the degree and the leading coefficient, because that's going to tell you what it looks like, partly. And you need to know the constant term. I'm going to be very quick here. Don't write this down, obviously. You could multiply out those two pairs of factors to get that. I'm just going to double check it. 9 minus 2 is 7x. We have negative 12 and negative 5. I think it's okay.
We have a different function.
This is not in your handout. This is just something off the cuff that I decided to include this morning. Thank you, though, Ryan. And then what you could do, and this is why we don't want to do it, is this. Oh, my goodness. 1, 2. Multiply those. Multiply these. And multiply these to get 9 terms, and then add them all together. You know, use the distributive property. It's a Math 10 problem. But we don't need to do that. And I'm going to write something that I think you need to become familiar with seeing. That is the important aspect of this polynomial function. That if I multiply, and I'm going to double check my multiplication here, but if I multiply the highest degree term in each factor, 2 times 3 times 1 times 2, 2 times 3, that's 12, and I have x times x times x times x, I get 12x to the 4, right? Okay. If I multiply now the constant term in each factor, I have 3 times negative 1, which is negative 3, times negative 6, which is 18, times negative 5, which I believe is negative 90. I'm pretty sure. So what does the graph look like? You don't know yet. But you will need to look at the leading coefficient, the degree, and the constant term. Everything else is just fluff. It doesn't tell you anything today. So when we go to this question, well, I mean, we should write this out. I don't think everybody needs to do this, but I think enough of you will need to do it that we should all do it. If you want to determine the leading term, then you have to multiply, and this is tricky, the highest degree term of each of those factors together. Now, this 3 is a factor. Factors are things that get multiplied by other things, which are called factors. You're not going to see that definition in a math textbook. That's just me. So what is the, for the degree, what is the, I'll be consistent here, what is the highest degree term of this factor over here? Well, it's 5x squared. What is the highest degree of this factor here? It's 4x. This is 4x. The highest degree of this factor is 3. Even though 3 is a constant, in that factor it is also the highest degree term. So I multiply those out and I get 1680. I think I get 240x to the 4. So you're checking the arithmetic in terms of the number. You're getting positive 240. And then I have x times x times x squared, which is x to the 4. Sorry, I'm not writing that there. My mistake. Because this is just degree, right? So the polynomial will be this, plus some stuff, which we really don't care about. And then the constant term, I'm actually going to adjust something here just to be, you get it, but I want to be technically correct. I didn't mean to imply, although I did say it, that the degree is the product of those yellow things. That's not the degree, that's the leading term, right? That's this thing. The constant term, however, is, without a doubt, found by multiplying all of the constant terms of the factors. 3, negative 1, and 3. That 3 in that first factor is both the highest degree term in that factor. It contributes to the leading term. but it is also the constant term in that factor. So what are we going to get here? You're going to get 3 times -1 times -1, which is still 3. You're going to get 9. So there will be plus 9 here. And now we can answer the question. The constant term is 9. The leading coefficient is positive 240. The degree is 4. And we're done with C. Are we okay there? Okay. Example 3. And I'm perfectly aware that there's no example 1 here. Again, I redid my notes last night. I got rid of something, and I forgot to renumber. Consider the polynomial function p of x equals 4. Why is this called a constant polynomial function? Well, there are a number of reasons. 1, it's simply y equals a constant. 2, the value of y is always going to be the same regardless of what x is. Okay. So one way to explain why the function, which is p of x, also known as y, is called a constant, is it doesn't matter what x is. The function, y, is constant. What is the degree of this? Well, 0. Do you agree that a quadratic function is degree 2? Shouldn't even need to write down a quadratic function. I will in a second. I'll show you one. Do you agree a linear function is degree 1? Okay, so grade 10, you focus all your attention and energy on linear math, linear graphs, linear functions. Grade 11, you expand your horizons and you do a lot with quadratics. So you work, and this degree 0 graph you encounter along the way, but grade 10 is mostly degree 1, grade 11 is mostly degree 2. Well, what grade 12 is all the other degrees. 3, 4, 5, 6, 7, 8, 9, 10. You'd probably never be asked about a degree 10. So I would like you to turn the page, please. And let's extend this into what I was just talking about. We have just learned, and you can look up here, this is all filled out on your chart, that when you have p of x equals c, we usually use c. It's just some number. Okay? And I don't want you getting ahead of me, please, on your graphing calculator here. If you look at p of x equals c, that's just some number. That's like p of x equals 4. So that is degree 0, and there is a name that we call it. It's a constant. And the reason why you need to know that is you might be told in a question that one of the functions is a constant polynomial function. If you don't know what that means, then you don't know where to go. In grade 10, we would usually write y equals mx plus b, where m and b are parameters. They're numbers. They're coefficients is what they really are. And m happens to be the slope and b happens to be the y-intercept. Well, here we just use a and b. Okay? And that's called a linear function. You'll notice here that it says that a is not equal to 0. The reason why, by definition, a linear function can't have a equals 0, because if a is 0, then 0 times x is nothing, and there is no linear term, so it's actually not a linear function. It would be a constant function. So that's why in all of these we're going to be saying a is not 0. And this is very familiar to you, I hope. We actually do use the letters a, b, and c. A is not equal to 0. That's a degree 2, and that is quadratic. I'm really not sure what just happened there. And that is quadratic. Capiche? Okay. Well, you are expected to know that when you have a degree 3 polynomial function, which would look like this, so a, b, c, and d are just the coefficients of all of the terms, it's called cubic. You're expected to know that a degree 4 is called quartic. And you are expected to know that a degree 5 is called quintic. And That's because you might get a written response question on my exam or the diploma exam that says, sketch the graph of a quintic polynomial function with the following properties. And quintic look different than quartic, and they look different than cubic. So you need to know these. Quintic is maybe stretching it. I'll be honest, it may be a bit of a lie I just told you. I've never seen the word quintic on a diploma exam, and I would never use it. But definitely we use quartic all the time. Okay, so your teacher will graph a variety of polynomial functions on the smartboard. In the charts on the next page and this page, we want to summarize the general rules that describe the characteristics of the graphs for these different types of functions. I am not going to be writing much down, particularly on this big chart that you're looking at on page 2 of the unit handout. Okay? That's me. So we're going to look at graphs of polynomial functions. The first polynomial function we're going to be looking at will be a fairly basic one. It's going to be a constant polynomial function. Then we'll look at linear, then we'll look at quadratic, all the way down the line until we get to quintic. And, you know, if I gave you a list of these polynomial functions, you could certainly use your graphing calculator to plot them, but I've got them all loaded up here. So if I graph, say, f of x equals 10, you'll see the equation of each polynomial function pop up somewhere on the graph. It's in the top right corner there. I hope it's clear why that's a horizontal line, because y is always 10. And we're going to come up with a general rule about x-intercepts, okay? Constant polynomial functions are an exception to the rule. Okay, so I'm going to tell you something about this constant polynomial function right now, and it's that it has 0 x-intercepts. Okay? It's no coincidence that the degree of this function is 0 and there are 0 x-intercepts. That's kind of a general rule. There's tweaking that needs to be done to that rule. It's not that simple. The reason why this is a total exception to the rule is there is a constant polynomial function that has x-intercepts. In fact, it has an infinite number of them. And it's f of x equals 0, which is the x-axis. So once we get that out of the way, we can move on and talk about the rule. So that is a constant polynomial function. You should make a note that the degree is telling you it has 0 x-intercepts. Here is a linear polynomial function, a linear function. And I hope you would agree, as long as the slope isn't 0, and if the slope is 0, it's not linear, it's constant. I hope you would agree that every linear function in the universe has one x-intercept. You cannot draw a non-slope 0 line. You cannot draw a linear function without it crossing the x-axis in exactly one place. Well, a linear function has a degree of 1, and there's one x-intercept. Okay. What about a quadratic? Well, there's an example of a quadratic. You can see the equation of the quadratic function up there. It doesn't matter what it is. I don't even need to show you the equations. I'm not going to lie to you. This is a quadratic function. And a quadratic function is degree 2. And there are 2 x-intercepts. So a degree 0, which is a constant, has no x-intercepts. There's an exception to that, of course. A degree 1 has 1 x-intercept. And this degree 2 has 2. But I have a question for you. Does a quadratic function have to have 2 x-intercepts? No. If I use my knowledge of translations from this course, I can translate this up a particular amount. I can translate it up a particular amount. I know the precise amount to translate it up, and I've hidden that number from you. In the legend, you don't know the equation of this. But you know there has to be a function where there would be 1 x-intercept. This has to do with Math 20 and the discriminant and all that stuff. So the quadratic function can have 2 x-intercepts, or it could have 1. Does it have to have 2 or 1? No, it can have 0. It can have 0. If I translate it up enough, it can have 0. So a degree 2 polynomial function can have any number of x-intercepts from 0 to degree 2, to 2, 0, 1, or 2. You might want to give some thought as to why this graph, this shape, it's possible for it not to cross the x-axis. It's possible for a quadratic to have 0 x-intercepts, and yet it's impossible for a linear function to have 0 x-intercepts. Okay? We'll come back to that. What about a cubic? Well, let's go to a cubic. I don't think it's a big surprise that I am showing you a graph here that has 3 x-intercepts. And it's cubic. If you look up there in the top right corner, it's a cubic polynomial function. So a cubic polynomial function can have 3 x-intercepts, no more than 3. And maybe we can come up with this general idea now. You know, the quadratic can have no more than 2. The linear can have no more than 1. So the degree is really telling you the maximum number of x-intercepts that are possible. But is it possible for this function, this shape, to have fewer x-intercepts? Well, if I shift it up very delicately the right amount, I can get 2 x-intercepts. So this degree 3 polynomial function can have 3 x-intercepts, or it can have 2 x-intercepts. Can it have 1? Well, I just shifted up a little bit more. There are other ways to accomplish this, but yes, it can have 1. Can it have none? What is it about this graph, and I see you guys shaking your hands, that this type of graph must cross the x-axis somewhere, but this type of graph doesn't have to cross it somewhere? What's the significant difference in the shapes of the graphs?
The direction of the arrow.
The direction of the arrows. We're going to call the arrows arms. In this type of polynomial function, both arms are in the same direction. It's exactly right. But in this type of polynomial function, it doesn't matter, you know, whether we're talking about 2 x-intercepts or 3, the arms are in opposite directions. And if you start down at negative infinity and you know, wobble up and down all you want and then go up to positive infinity, you have to cross the x-axis somewhere. So it's possible to have 1 with a degree 3, or 2 with a degree 3, or 3 with a degree 3, but not 0. So we might maybe learn something from this and say that a degree 1, if you look at my arms, a degree 1 has arms that go in the opposite direction. So it can have 1 x-intercept. A degree 2 has arms that go in the same direction, and that means it can have none, or 1, or 2, because it's degree 2. A degree 3 wobbles up and down once like that, and the arms are in the opposite direction, so it can have 1, or 2, or 3, but not 0 because the arms are in the opposite direction. You might then suspect that a degree 4 will have arms in the same direction. It's flipping back and forth, isn't it? It's degree 1 is opposite directions for the arms, degree 2 is same direction, degree 3 is opposite. Well, you would be right if you said degree 4 has arms in the same direction. And that's why this lesson is about your general understanding of the shapes of the graphs. If I tell you we have a degree 4 polynomial function, you don't know whether there's going to be 1, 2, 3, 4 x-intercepts or 3 x-intercepts. And I accomplish this by shifting it down a little bit. That's still a degree 4. It's got those wobbles that correspond to a degree 4. Each time we go from, well, I'll start with quadratic, has kind of one wobble. I'll call it a wobble. One change in direction, because it's going in 2 directions, down and then up. Hey, degree 2, it goes down, then up. One directional change because there's 2 directions. Degree 3 goes up, then down, then up. 3 directions. So 2 directional changes, which I call wobbles. Don't use that word on an exam. Okay. Degree 4 goes down, down, then up, then down, then up. 4 directions. The degree is telling you how many directions the graph could potentially have. And I say potentially because there's subtleties to that it doesn't have to look like this. It can look different. We'll get to that later in the unit. But if I shift this the right way, this is degree 4, I can have 3. It's possible for me to only have 2. It's possible for me to have only 1. And it's possible for me to have none because the arms are in the same direction. And I hope you're learning that there's a pattern here. When the degree of the polynomial is even, an even number, forgetting about constant polynomials, when the degree is 2 or 4, the arms will be in the same direction. Now, I don't believe I have degree 6 loaded up, but degree 6 would also have arms in the same direction. If I go to degree 5, it's probably no surprise that I can construct a degree 5 polynomial function with 5 x-intercepts. Does a degree 5 necessarily have to have an x-intercept? Yep, because the arms are in the opposite directions. You can't go from down here to up here continuously, and all polynomial functions are continuous, without cutting the x-axis somewhere. But if I shift that in a particular direction, in this case I think I went up a certain amount, I can get 4. I can get 3. And this isn't me just using my imagination and sketching things. These things, if I look at 4, these things have equations. I've just worked out what the equation is that will produce that. It isn't that it's just possible to draw it. It's possible to get an equation that draws it. So I don't want you to just think I've cheated the system here and drawn something. I haven't drawn anything. 3 x-intercepts, 2 x-intercepts. At 1, there's a couple of ways you could have gotten 1 here. But not 0. Why not 0? Because the degree is odd, and if the degree is odd, the arms are in opposite directions. This is what we're learning today. I'm kind of summarizing as I go along. So, I'm not going to write anything here. I'm just going to say something. That a constant polynomial function in terms of x-intercepts doesn't have any. There is that exception where you could have y equals 0, in which case there's an infinite number, but that's not following the pattern that I think is important. A linear, which is degree 1, must have 1 x-intercept. It can't have more because the degree is 1. The degree tells you the maximum number of x-intercepts, again, ignoring the constant polynomial functions because that's not a rule there. But it can have a maximum number that matches the degree or less, but in this case, since linear is an odd degree, the arms are in opposite directions, it can't have less. It must have 1. Quadratic is an even degree polynomial, so when we graph it as a function, the arms will be in the same direction, which means it can have no x-intercepts, or any number from none up to the degree of 2, 0, 1, and 2. A cubic is degree 3, so the maximum number it can have of x-intercepts is 3. By the way, if this were a cubic equation, that would mean the maximum number of solutions is 3. But it doesn't have to have that many. It can have less. It can have 2. It can have 1. But it cannot have 0 because this is an odd degree and the arms go in opposite directions. What that means, everybody, is if this were an equation, every cubic equation in the universe has at least one solution. Just like every linear equation has a solution. But last year you learned quadratic equations sometimes don't have solutions because graphically they correspond to no x-intercepts. Every odd polynomial equation is solvable, but not every even one is. And I know that many of you are going on to take calculus, and I just mentioned some of these things because they might be helpful next semester. Quartic, well, a quartic is an even degree, so it can have no x-intercepts because an even degree means the arms are in the same direction. And quartic is degree 4, so it can have any number of x-intercepts from 0, integrally speaking, up to 4. I mean, I don't think I need to say that. You know you can't have 1.38 x-intercepts. You can have none, 1, 2, 3, or 4. And then the pattern continues. This is quintic. It can have a maximum of 5 and a minimum of 1, and any number in between, whole number in between, natural number, whatever you want to call it. But it cannot have 0 because it's an odd degree. Okay. So let's turn the page now. What this means is that even degree polynomial functions will have an arm that goes up in quadrant 2 and an arm that goes up in quadrant 1. I'm not drawing what it looks like in between, because if it's degree 80, it's going to come down and up and up and up, up and down and up and down and up. It's going to do it a lot of times. There's going to be a lot of wobbles. Or, and we haven't seen this yet, but I will show them to you now. I don't know if you noticed this, but all of my even polynomial functions had both arms up, right? Well, let me show you some even polynomial functions that have both arms down. So just because we've only looked at both arms up for even doesn't mean both arms can't be down. And that means that these even polynomial functions might look like this in terms of what we call end behavior. By the way, I want to point out to you, and you need to add this, if it looks like this, the function, don't forget function is another way of saying y, must have a minimum value. If both arms are up, I don't care what it wobbles like in between, there has to be a lowest point to the graph of the function. And over here, if you have an even degree with both arms down, this must have a maximum value. I'll put the function. The function has a maximum value. Odd degree, just before I draw them, you know, if both arms extend in opposite directions, that means one of the arms goes down to negative infinity. There's no minimum. There's no bottoming out of the function. And the other arm goes up to positive infinity. There's no peaking of the function. So it will either look like this, and again, I don't know what it does in between. We're going to see weird situations where maybe what it looks like is this. It doesn't have to be up, down, across the x-axis. There are strange things that can happen, well, in mathematics, right? Things are not always very simple. But it could be that instead of the left arm down and the right arm up, you could have the left arm up and the right arm down. Whoops. Down. There are no extreme values here for these functions. There's no maximum value to a cubic function. You just keep putting in different values of x that are bigger and bigger and bigger. The result will either get bigger and bigger to infinity or bigger and bigger to negative infinity. Positive leading coefficient, negative leading coefficient. I'm going to assault your senses here. I'm going to tell you right now, I'm going to leave the constant one out. That all of these polynomial functions, even though you're not going to see any of the equations, I don't know how to get rid of that. I'll just move it out of the way. I think I can. Yeah. There is something that all of these polynomial functions, and I know that's a visual assault on your senses, all of these polynomial functions have something in common. They all have a positive leading coefficient, I will tell you that. But the graphs all have something in common because of the fact that the leading coefficient is positive. Anybody see it? What is it?
For every even degree, they're both pointing up with the arms, and for the odd degrees, one of them is pointing down to the left and the other is pointing back to the right.
Okay, so what we want to do is come up with a rule that doesn't say odd and even. The bottom line is you've just told me that on the right-hand side it's going up. All of these arms on the right go up. Whether it's odd or whether it's even, these I mean, it's a mess here, right? But you can see the arrows all on the right-hand side of the screen pointing up. So what we learn from that is regardless of the degree except for 0, I have to keep saying that, regardless of the degree except for 0, regardless of whether it's even or odd, the right arm will be up. Now, if it's a positive leading coefficient that's even, then both arms are up. If it's a positive leading coefficient that's odd, then the right arm is up and the left arm is down, because the right arm must be up. Here are, and I didn't go to town like I did with the other ones. I didn't give you like 15 or 20 of them. Here are 5 with, you can see I've got negative in front of the leading coefficient here. 5 with negative leading coefficients. And the left side is just all over the place because it depends on the evenness or the oddness. But the right side has all of these lines pointing down, all of these curves pointing down. Which means if the leading coefficient is negative, all that tells us is the end behavior on the right is negative. If it's even with a negative leading coefficient, then both arms will be down. If it's odd with a negative leading coefficient, then the right arm is down but the left is up. And then if it's degree 5 with a negative leading coefficient, the arms look like this, and you can tell me how many x-intercepts there might be. There's a couple more things I want to talk about here. What about the constant term? I'm going to go back here to all of these positive leading coefficient ones. And I'm going to pick some that we can see the equation of, that I haven't hidden it from view. For example, I'm going to pick y equals 4x minus 9. And I've moved my legend out of the way, so I just want to get it back. I don't know quite how to do that. I think the best plan is to just close this and open it. So here is y equals 4x minus 9. And you can see in the top right corner, the constant term is negative 9. Take a look at the graph. Here is a quadratic. The constant term of this quadratic happens to be negative 5. Take a look at the graph. I hope you see it almost immediately. We're talking about the y-intercept. When I take a look at this cubic, that's underlined in red and graphed in red, the constant term is 8, the y-intercept is 8. This should make sense to you, because how do you find a y-intercept? You change x to 0. And if I change every x to 0 here, all I'm left with is the constant term. So the idea here is that a positive constant term means the graph will cross the y-axis someplace above the x-axis. It will have a positive y-intercept. A negative constant term means the graph will cross the y-axis in a negative position, below the x-axis. And as I said, I changed my note package last night and I was running out of ideas. I think if I were to redo this, I would have just left this bottom note in and forget about the graphs. Because the important aspect is the constant term is always equal to the y-intercept. So this is why, if you go to the title, the cover page of your unit handout, I say 2 things that are odd. And this picture was a serious picture in 1970, I want to say 77. I think this is Saturday Night Fever. Classic movie. You gotta find out what it's about. I'm just kidding. It's so cringeworthy now. But John Travolta is odd. This is peculiar, isn't it? But the way he's holding his arms is also odd in terms of a polynomial function that would be cubic. Right? So I will very often say, oh, that's a John Travolta function. Okay? As I said, this is serious. People did that. People danced like this and dressed like this. I had shoes like that. I'll show you a picture one day. Yeah. Ooh. This isn't somebody trying to make people laugh. This is somebody trying to be popular. Anyway, I think you get the idea. We don't need to look at that.